Hi everyone, you're with McRae of Réveil, and today the plan is to explore the STL algorithm. The STL algorithm stands for Seasonality-Trend and LOESS. The LOESS is a non-parametric regression method, and at the end of this session, we're gonna implement the algorithm in a rough manner directly in Jupyter Notebook. The motivation behind this is first and foremost, to learn what is the STL algorithm. I've seen it used quite a lot, but I never really had the time to dig into it. So I had to assume that it was used in a reasonable manner. However, as soon as I started looking into it, what I noticed was that it used methods in a way that are very obscure. We're talking about compounding rolling average, the LOESS, the decomposition between seasonality, trend, and the detection of outliers and weighting of outliers in the inner and outer loop. This all makes it quite mysterious. Why use the STL instead of a specified regression model, for example? So today that's the plan. I was planning to do this as a kind of a 2 hours, 4 hours statistics marathon. But let's go this way. Let me comment over the footage that you're now going to see and try to give you the background that you would need if you wanted to follow along or implement a similar algorithm by yourself. Now, what you can see is I'm already looking into the MSTL PI file from the stats models GitHub. There, what I quickly noticed was that I needed to cut my ambitions a little bit short, and you'll see this. But the first thing you see here is that the MSTL implements the STL. And what is then the MSTL? Well, roughly it's a version of the STL where multiple seasonalities can be accounted for. So to be clear, here I keep things simple and I only consider a single seasonality. And that is to say that you might have, for example, a time series with a weekly seasonality, yearly seasonality, something you'd see, for example, in retail where the Sundays are a lot slower than the Fridays, but also where the Christmas period is way more intense than the summer vacation period. So where you would have these two seasonality. Here I only focus on one and I simulate the data for it. But let's go on. So I was here studying the STL implementation and I noticed the use of a POIX file. This is a version of Python, if I understand it correctly, that's used around line 200, 203. It uses C types. So the Python is compiled in C before being run, and this makes it a lot more efficient. So here we're not gonna bother with this kind of efficiency at all. In fact, I noticed a lot of detail in this implementation that just go beyond what I was willing to do in a couple of hours. My goal here is to understand the algorithm better. So the approach I'm taking instead is to look at the original paper from the early 90s, actually. But this is something that is still very relevant. In any case, what you see here are the two really important parts for the implementation, the inner loop, and I think a page or two below, you have the outer loop. And the idea is that you will want to run the inner loop multiple times so that you can remove or rather weight observations according to whether they fit the detected seasonality and trend pattern. So in the inner loop, you do the decomposition, and you'll see one run of the inner loop in some case is enough to get a nice looking decomposition. And what I'm going to look at here with my Claude client is the definition of a cycle subseries and then the requirement to add n of p values on each side of the study time series. For the cycle subseries, each subseries is looking at a component of the season and then jumping directly to the next component until the end of the time series. So a component would be, for example, January of 1958, and then we jump to January of 1959, and so on until the end of the time series in the paper 1985. We'd extract each of those Januaries, and this would be our cycle subseries. And then it's just a question of fitting a smoother such as the LOESS on this subseries. We do this for every component of the season. Well, here we have monthly data as in the paper. So we'll have 12 components per season, 12 months. So we do this 12 times, and then we reassemble these cycle subseries. And on each side of the reassembled series, so the composite of all the LOESS we fitted, we predict or we infer the 12 smoothed values on each side. For each subseries, this means that we'll infer a component before the start and a seasonal component after the start of the time series. This gives us 12 inferred components on each side. And why do we do this? Why is this necessary? That is just because we do a series of rolling or moving average, and each of these rolling average will reject some values on the extreme of the time series. So it's a trick to get the original length of the time series back after we do those moving average. And the next thing I take my attention to is the computation of the remainder in the outer loop. This is the main part of the outer loop, computation of the remainder, and then the weighting of each observation of the time series according to how extreme this remainder is. And if you look at the equation for the remainder, it is very simple. It is the observed values of the time series minus the calculated trend minus the calculated seasonality component. And then there is a small equation where we give more weight to observation that have a remainder that is closer to zero. Why this is done? Well, how I see it is that you want to put less weight on possible outliers or moments in the time series where some kind of external event occurred. You want to focus on the signal behind the seasonal and trend component. As a kind of check, I looked at the rest of the papers for other piece of information that might be useful. One thing that I saw readily is the kind of plots I could expect from the decomposition, namely a graph for the seasonal component, a graph for the trend, and a graph for the remainder. Then once I'm satisfied, let's say, with the reading of the paper, I did some setup on my computer and I'm going to create a project just for this experiment where I'm going to use the generated data from the stats models package. You see it in the comment on top of I think it's the STL implementation. I'm going to copy this and I'm going to try from the paper relying on to reproduce the algorithm. So here I go in this code. I also set up some quiet Python module with Mamba or micro Mamba to be exact. I will copy the data generation code. And what I do here is makes this easy, is I take the commented code block and simply convert it in readable code. Voila. The first step, once I've generated the data, is to look at how it looks. I want to see that there's a trend and a nice seasonality. And here you'll notice that there is weekly seasonality data. In the next step, I remove this weekly seasonality from the generating process. One thing that's nice to do is, before I start actually reproducing the algorithm, is looking at what happens with the original implementation. This all seems to be okay. I then plot the results, and voila. Then I have something I can use to compare our later implementation with. I have a reference point. Looking at the decomposition graph, there's a few things you will notice right away, which I find are quite interesting. First, the trend is not linear function. It's not a straight line. This is a nice feature of the LOESS, where if there is some change in the underlying trend, as you would expect from any kind of data really over a period of time, that the trend will not be constant, this can be modeled here. And we also use the same or a similar LOESS for the seasonal decomposition. And here also, although it's a bit subtle, there will be a change in those seasonal bumps. Now I'm going to start the implementation. And one thing I like to do there is sketch things a little bit because of those cycle sub-series. I mentioned that we'd have to split the series into the seasonal components. And there I want to be sure that I do this split programmatically as easily as possible, that my life is as easy as possible. And you'll see that with NumPy, this is very easy to do with the indexing that's allowed by the modules. But here I see that, for example, every year or every bumps, I'll look at the specific point and then I'll draw a kind of line a sort of continuity between these points. And out of this, I will remove a trend signal. This is part of the inner loop of the algorithm. And I'll be left with so-called seasonal bumps. And now, as I was sketching this, indeed, I noticed the weekly seasonality, which I would not bother with. So I remove it. And here I start actually coding, actually doing some work in the implementation. It appears as if the length between two seasonal components was 24. So I go with it. I set n of p to 24. Here I'm looking on one end at the series, but also at where I can take the slices I need. Here I do with this double columns. I can look at the series by doing these jumps of 24 days. And these jumps or the length of the season is simply how the data was generated. There's nothing special to it. We're not looking at year. We simply arbitrarily decided that a season would be of the length of 24 observations. So every 24 observation, for example, we get at the same moment of the season, at the same bump. Now I'm doing a bit of live coding, just looking at whether I get an error here. Indeed, no. So that's excellent. I, of course, following the paper, need to use a non-parametric regression method, the LOESS. I'm simply going to take an implementation from stats model, but we'll soon see that this implementation does not have all the needed feature for the full algorithm. So we'll have to get a bit creative, let's say. Once I understand how to implement this LOESS, one thing I need to do is add these -1 and +1 values to the x values. And this is the inference I mentioned earlier when I said that we need to infer past the extreme of the time series due to the moving average computation. So this is done as simply as this. I do this for every one of the 24 seasonal components, and that's it. Then my LOESS will be fitted on the actually generated data, but inferred on those x values. It will give me what I need. I then add this line of code to define impute IDX. And here, what I'm doing is for every one of the seasonal components, identifying every element indice of the original series, where I will assign the output of the LOESS regression, the original time series with those extreme x values added, of course. I then have to implement a so-called low-pass filter. This is done with rolling average in the algorithm, or multiples, actually. We do 3 in the inner loop. And funnily enough, I actually did not know how to do this. And here I found this method very interesting. We use a convolution to get those rolling average. So we're going to convolve the C array with the fitted seasonal component against unit, or rather fractions of the window size. And the window size, well, that's just the size of your moving average. So doing this, since the convolution is a kind of a rolling sum, we get this rolling average. Because this is a learning exercise and I don't want to copy and paste or simply let the AI do all the work, I do write the function myself to try to appropriate it. While I'm writing it, I try to consciously think about the steps. Looking at the documentation for convolve, I notice that I need to use the valid option. Why? Because when there's not all the information necessary for the moving average, namely at the extremes of the time series, in this case, I want to get null value. After a bit of research, I actually implement this low-pass filter in the algorithm. I do it outside the loop, of course, because the C array containing the seasonal components has already been defined. And you'll notice I start with 2 moving average on the C array, and then I take a last moving average with a window of 3. Why 3? Good question. I suspect it's been decided on because of some experience. And in the paper, what this composite of moving average useful for, it removes the trend signal from the seasonal decomposition. And to check this, to verify this, well, you can do it graphically as I'm doing here. In orange, you see the moving average trend, and the blue line is the original C array. And what we're going to do now, to get the seasonal component, is remove this orange line from the blue decomposition, from the C array. I quickly verify verify that this makes sense. And as you can see, we get this kind of sinusoidal bumps without the trend. As we're getting closer to the implementation of the outer loop, I look here at how the remainder weights are computed. And there's only two things that are really important to remember here. It's that the remainder, the larger they are, the lower weight the observation will have in the next inner loop iteration. And the second thing is that those weights are between 0 and 1, and they are fed in the LOESS algorithms, both for the trend and for the seasonal decomposition. As usual, I do sanity checks by graphing the intermediary outputs from this implementation. Here I look at the remainder array, and I notice this U shape, already a bit worrying to me, but actually it shows a kind of bias that is positive in the middle of the series and negative on the extremes. The second thing that I noticed looking at this U-shaped graph is that the extremes will take less weight in the next iterations of the inner loop, now because the remainder are larger in absolute terms. Again, I have some fun in implementing the B-square weighting functions myself, a bit of live coding, and because remainder values that are too extremes get a weight of 0, I make a mask here where I look at if U is larger than 1, I will simply return 0 at those points, 0 weight. To be 0, a value has to be quite extreme. And we're referring to h, the denominator. It has to be larger than h, and h is 6 times the median of the remainders. So most, except the most extreme observation, should still be included in the decomposition. Now I find myself in a bit of a pickle because I need to incorporate those robustness weights into the LOESS, but the stats model implementation does not allow this directly. After quick consultation with the cloud assistant, I decided to look into scikit-misc, which might have the options that I need for those weights. A quick look at the documentation of the LOESS scikit-misc function is not very useful, so I decided to dig a bit further. In the end, I just asked the AI for an example implementation using this scikit-misc package that allows for both distance weight, like those of stats model, and robustness weights. Now, I will do some modification of this implementation, but it really unblocked me. So I set the span to 2/3, and then I test the implementation with the robustness weights I got from my first iteration of the inner loop. This, at first sight, seems to work. Now let's plot it. And indeed, I get a time series so I go back to the initial inner loop and I replace the LOESS with the new implementation. It doesn't work, but when things work the first time, I'm always worried. And indeed, it was because I forgot to assign weight to the extreme X values. I also need to take subseries from the robustness weights. So this is now done. What can go wrong? And it seems like it worked. Nice. At that point, I basically achieved what I wanted to do, which is implementing the different component of the STL algorithm. But there's no outer loop. The outer loop up until now has just been manual computation. So I decided to really write a function that does the implementation of the whole algorithm. I don't bother here with specific settings like the length of the seasonality, the type of seasonalities, etc. My only interest here is to make sure that I understand how I could implement this algorithm in practice. And this is basically putting the pieces together. In this day of using AI to do a lot of coding, it's also a good exercise to stop and to write things down yourself. Let's go on. Yeah, you'll recall I implemented the inner loop already, so let's not repeat ourselves. The main difference here is that I need Y to be detrended at the beginning of each iteration, and I do this at first with a trend array of only zeros, and within each inner loop, this trend array will be updated. Now here we go. What's missing? Well, the robustness weights must be included in the outer loop. I will have most of the required functions from earlier. Well, how could I forget the low pass filtering that I need to do after each seasonal decomposition to extract the trend signal? I'll also use this L array to estimate the trend. I then declare the subcomponents, the seasonal array. Then we'll have the trend array, which, if I'm not mistaken, is the observed value minus the detrended seasonal component. And then now we define the return values so that we can somewhat reproduce the plots I showed initially in this video. The first run of the function fails. I'm trying to get the length out of an index. Doesn't really make sense. And here we go. Let's get those components. Hopefully make a plot. I'll spare you some of the coding. But yeah, voila. We have a plot with a nonlinear trend, the seasonal bumps, and the remainders. So that's it for today. This is what I will call kind of a statistical marathon, where I just try to explore a topic or understand something better. And you can expect more of this in the future. It was certainly very enjoyable to make, and I wish you a very nice day.